Dr. Nijisha Sajan, Assistant Professor from the Department of Biomedical Engineering, SRM Institute of Science and Technology, Tata and Little. So in this course, Principles of Medical Imaging, we'll be seeing Unit 1, X-ray Imaging and Digital Radiography. In this unit, we'll be covering in this session the production of X-rays, specifically characteristic spectrum, stationary X-ray anode tube, rotating anode tube, X-ray machine, high frequency generators. Let us go to the session. So now let us see what do you mean by characteristics X-ray spectrum. So already in production of X-rays, we have covered what is brainstorming spectrum. So let us see what do you mean by characteristics X-ray spectrum. So now the same atom, you assume that the high energy electron is accelerated electron is coming and interacting, but not with the nucleus or away from the nucleus. Instead, it is going and attacking the electron. Now what happens is if this energy is more than the binding energy of the electron here, so you have the K shell, L shell, M shell. So the electron is in the K shell, and if this energy is more, if this energy which is being coming of the energy of the electron is more than the binding energy, this energy gets popped out. So it removes that from the shell and it goes outside. This is the ejected K shell electron. Whatever is the balance, it just gets rebounded. Okay, so it just pushes this out and it moves away. Now what happens when this happens? What happens now is there is an empty vacancy here. The atom cannot remain, what do you say, it is not stable if there is no electron in the lower shells. Okay, or that we have seen, remember? So K shell, L shell, M shell, electrons, it has to be filled. The lower energy, lower shell electrons is K shell, electrons have to be filled. So to fill this, what happens is the higher shell, that is your L shell, that electron comes to fill this here. So this L shell electron jumps here. Now this jumping of this electron, from this to this, there will be a difference in the energy. K shell is high energy, L shell is little bit lower energy. Imagine here, you can see here, K shell is 69.5 joules, kilo electron volt, and for L it is 12. So whatever is this difference energy, so this is shifted here, whatever is the difference energy, that difference energy is being produced as a X-ray. This is called as a characteristic X-ray. Very simple. Okay. So the previous condition, it is nothing but the electron is going to go directly, hit the nucleus, and it is going to just go away. In that case, what happens? Whatever is this deceleration in the electron, that is being produced as an X-ray. Here the electron is going, knocking out one electron, that one electron, this one, the previous electron, from the L shell electron, it is going to go and refill it, and that refilling is going to produce an X-ray outside, and that is called as a characteristic X-ray. Now, if you note here, for Bremsstrahlung spectrum, we had different possibilities, correct? What were the possibilities? The electrons can go directly to the nucleus, it can go sliding close to the nucleus. Other condition was it can go away from the nucleus. So we saw that the spectrum was more widespread. Here, this is not possible. Why? Because this K, L, M and all is fixed. So for tungsten, K, L, M, the energy levels are fixed. So whatever happens, the energy will always be this difference in the different shells. So if it is going and attacking L, then imagine M minus L, whatever is the energy difference, that radiation only, that energy level only will be your X-rays. That is the main difference between them. So based on this energies only, we decide what type of target atom you want. So if you want high energy, based on that you need to select this KLM. Okay, based on KLM you can select. So these are the available: tungsten, molybdenum, rhodium. So whatever I have told, just I have explained here. They are discrete X-ray energy peaks. Okay, how is that peak coming? Because of the difference in the shell. And why do you call it as characteristic? Is based on the material. So the material, like we saw here it is different, here it is different, here. So based on the material, the characteristic X-rays will change. So you can see here both have been shown. So if you have a spectrum, you can have this blue color, which is your Bremsstrahlung, and this is your filtered Bremsstrahlung. Okay, actual will be something like this. Here it is a filter. Whereas if you see characteristics based on what type of material, tungsten you're using, how many such materials are present, based on that you have the character. They are more impulse type of response. Now, with continuation with the production of X-rays, these are the different types of tubes. Okay, so this is the tube that we saw discussed. So this is the envelope, and you have the cathode, you have the anode, and then you have all the materials, all that. Now, based on this, based on how you want, how more energy, all that, we have two types. One is called as a stationary mode tube, and the another one is called as a rotating anode tube. The difference is the anode, the place where this electrons goes and bombards, that you can have it stationary, you can have it rotating. Why do you need a stationary rotating is, we'll see what is the concept, but then we'll discuss why the need. Okay. So this is a stationary. Simple is the anode doesn't move here. So how do you do it? How do you produce this one? All that is, it has a glass envelope. You have the cathode here. Cathode, the tungsten filament, the negative part, the cathode here. You have the anode here. In the anode, you have the tungsten target. Okay. So can you see here that it is a little bit tempered, like what is it, tapered type here. The reason why this is tapered is that for more surface area. So if I keep it straight, I have less surface area. If I keep it like this, I have a more surface area. And for more useful X-rays, I'm keeping this type of configuration. Okay, very simple. This is the whole ceiling and this one. So you have the power supplies going, all that. Okay. So we saw that you have to focus it, which is nothing but the cathode is nothing but the you have your the what to say, the filament tube. So you can see here the filament circuit which is about 10 volt you have, and 3 to 7 ampere it is. So it has to be very high current circuit. Okay, so only then your electrons will pop out. So this is how it is done, and it is in a groove type. Why is it groove type? Is so that they focus and the electrons are thrown. So you have to assume like the electrons have to be, it must not go here and there, it has to be focused in one direction. So this is how the focusing cup is surrounded it will be, and then you have the tungsten, whatever is filament, you have the filament you have. So once again, it is in a vacuum diode, and like I told you, this target is nothing but the anode part. Okay, the cathode, it's a filament which is of stainless steel. The filament is nothing but tungsten wire you have, and the tungsten wire only is going to produce amount of what to say, electrons. Okay, now why do I use always tungsten? Is tungsten because it has a high atomic number, which means I have more number of electrons present inside. That is the main reason why we are using tungsten filament. So I use a very good current and voltage, I get more amount of electrons produced. Another important advantage is that it has high melting point. Why? Because when you are giving so much of voltage, any material, it will heat up. The energy in it will not be able to, so it will get heated up. So in that case, I need to have this. It has to have a high temperature. Copper, it is an excellent thermal conductor. It performs a vital function of carrying the heat rapidly away from the tungsten target. So what do? Is we insulate it with the copper. The stationary, it is for small capacity X-ray machine. Very, very important. Why this? Why do we use stationary X-rays? Whenever I want it to be compact, I don't want many electronics. My aim is to produce a very low energy X-ray. In that case, I use stationary anode tubes. Now let us see the second type, which is the rotating anode tube. In rotating anode tube, the same setup except that the anode will not be stationary. It keeps rotating. So you have to assume that it is a disc. At one point, you have the disc to be shown, then immediately it will move like a cycle. So this part is a rotating type. So for moving this, you have a rotor. All others are the same. You have the cathode, then you have this part, which is the filament. The filament is going to throw out the electrons. All others are the same. So this picture looks very, very this one, but the concept is the same. Here only thing is you have a rotor, a rotating part. So what main thing is, like I told you, when there are X-rays, I need to produce positive, negative, or very, very high voltage. In that case, high heat will be generated. So what happens in stationary, this whatever is your stationary tube, here, this part gets burnt. Okay, so for that only they're using a copper anode, because copper it will try to release off the heat. We saw here it is a thermal conductor, so it will immediately release off the heat. Whereas anyway it will become heated up, it can melt, all other possibilities are there. So what we are doing is we are rotating the anode. So at one point of time, one, then next, like that. So by the time this rotates and comes, the temperature will get reduced, the next again like that. So you're heating, you're spreading it out, that's all. The anode is a disc of tungsten or a alloy of tungsten, and this it keeps reducing, and so when it moves around, temperature, no, the difference can do. So what is the rotation speed? Around 3000 to 3600 rpms you have, and it is tapered to 5 to 20 degrees. Again, the rotor, everything will be of copper to release of the heat, and then you have the anode system. So this is a high energy, so it must be lubricated because it is rotating, proper lubrication must be there and all this. So whenever we go for rotating tube, you have an extra circuitry. So it is usually high energy, but it is more complex system. Okay, so it is used in diagnostic and therapeutic applications, and it employs high milliamperes and low exposure time. So it has a high kilovolt and relatively low MA, and it is used in therapeutic. So if in case for this is what I want to say is, if it is diagnostic, it will be lower exposure time. Okay, if it is therapeutic, it will be of a higher exposure time. What about the energy values? High milliampere will be used for lower exposure, whereas low milliampere will be used for therapeutic. So this is just to show how this tapered angle will be. So when it tapers, when it falls, this is the amount of area which is getting exposed. So you can see the actual image of the rotating anode tubes. This is how it is. You can see here, this is the rotating part, the black cover, no, the tube and all are lead shielded so that it doesn't escape, no, your X-rays don't escape that. Okay. That we'll be seeing is X-ray machine. So we have seen how X-rays are produced. We are going to just include all that and form the X-ray machine. So very important part of the X-ray machine is nothing but your whatever is the high voltage supply units. Okay. So here you have the X-ray tube. For the X-ray tube, I need to give high supply. So for that, I need to give a high tension supply, and then this has to be rectified and it has to be given. Everywhere you have a kilovoltmeter and a milliampere meter, that is to measure the voltage and the ampere. The reason behind all this is to based on what application you want, which area you are doing, you can reduce the energy of the X-ray which is produced. Okay, this can be changed. So if you see here, you have the kilovolt selector. So based on this, the kilovolt will be given, and then here you have a timer and you have an exposure switch. Why do you need an exposure? X-rays cannot be given always because they are radiations. They can create ionization in your body. So whenever you need, only that time the kilo voltage will be supplied to this one, it will be enabled, and this will go inside. So if you see here, the other side you have for the high tension supply, you have the voltage compensator, and you have the other side for the filament. No, you have to heat up the filament to produce the electron. So you have the filament supply. So this is again taken from the mains, and here milliampere control is being taken. So based on this and kilovolt selector and the milliampere, you can decide the energy of the X-ray. This is the X-ray. This is the overall block diagram of the X-ray machine. So they have two parts you have. So the two parts, like I told you, is the high voltage, the step-up transformer followed by rectification, the milliampere meter, and the kilovolt selector. So all this, whatever I've explained, is given in this slide. So very important is that is all in kilovolt, and the filament is around 6 to 12 volt. But the only thing is the current will be higher, 3 to 5 amperes. So how do you generate this high voltage generator? So naturally you need to have a transformer. From the mains, this gets you need a high voltage transformer to double this and to bring it to 30 to 200 kilovolt. So you have a step-up transformers, and they have windings, all that. It will be usually 1:500, so that 250 volt is being converted into 125 kilovolt. So that much it has to double up. Okay. So it is immersed, this whole unit is being immersed in a special oil with the high level of insulation. All this is again for heat generation, all that. Okay. So if you see in an X-ray machine, the generator part alone will be a very, very big system. Similarly, one way is to produce a high voltage generator. that is to go for a high voltage. But nowadays what they do is they go for a high frequency generator. Instead of developing high voltage generator, we are going for a high frequency generator. It is nothing but you take the three phases and you multiply it. When you do that, what happens is the same frequency, when it gets multiplied, no, you get the same output as a high voltage generator. Okay, so if you see here, around 50 hertz is getting converted into 500 to 20 kilohertz. Okay, this is by using normal circuits you are going to improvise it. So as you increase the oscillation, what happens is the same output is being done, but by increasing the frequency or increasing the voltage. So the circuitry, everything becomes compact and it is more simple system. That is the reason why we are going for high frequency generator. So if you see here, this is the use of small transformers we use. This is the input. So this is just to understand the concept. You have the input voltage, you have the rectifier, you rectify it, you smooth it, and then you invert it. Okay. So in this case, the transformer, you amplify it, you rectify it, you smooth it, and you give it as a voltage. So the same concept happens here when you go for a high frequency generator. With this we will complete this session. Thank you.